Gauge how loud I need to speak. So is this sufficient? Oh, actually, I'm amplified now. Okay. All right, so I'll talk to you about Planck, the project I've spent some 13 years on working so far. And I will begin with an attempt to share some of the excitement of last week when we managed to launch. So we went to French Guiana. Final date was May 14th. And I'll start with a couple of highlights about the land. This is a place, the table map for the launch place we went to. It's remarkable. The space science in Guyana figures prominently amongst all the animals. It's mostly an Amazonian forest, as shown in this picture. Everything up to the horizon's green. This is the infamous Devil's Island. We've been on this one. That one is off limits. You cannot go on it. This is what the beach looks like there. Amazon mouth is somewhere here, and all the silt flows in this direction, so the water is actually really brown. Still, people go for vacations and actually swim in that. I don't know if there's any cosmetic benefits or not, but I didn't try. Natural wonders, we've actually experienced all of those. We've seen the leatherback turtles laying eggs. The parrot came, visited us at lunch. Toucan came when we were passing on that island and enjoying monkeys. So we talked to him and touched him, and the jaguar was behind the fence, thank God. And then, a day before the launch, we visited the Space Center at Kourou, clearly the biggest operation going on in Guyana. And we got a tour which started with going on the bus. And this was our first glimpse of the rocket that took Planck and Herschel out. Then we spent a couple of hours watching it rolling out to the launch pad, which was this position here. This is the set of rails on which it drives. That's the launch pad from the other direction. This is Ariane 5 rocket, a pretty magnificent achievement of French space industry. This is the one-to-one model of it, all 51 meters of it. Here, this little blue blip you see is a full-size human silhouette, about almost 6 foot tall. So 51 meters, expandable to 58. Extremely powerful rocket, can lift 5 tons. Typically, it lifts 2 satellites because there are very few satellites which are as heavy as to fill the whole cargo with the weight that it can carry. We have been then taken inside the assembly bay from which our rocket rolled out to see the one that's going to fly in July. So this one is going to take a commercial satellite in July. You'll see 2 people. That's about 2/3 of a rocket kind of visible. They took us about 300 meters from the launch pad. This is our rocket. That's what it looks like. That shows that we're really in there, and the zoom on it. That was close enough to get equipped with gas masks and stuff. Wasn't very reassuring, but it did not explode. And then the day of the launch came, and it was terribly exciting. We got up very early. The buses were collecting us at 8, and just as we made it to the parking lot, this is what came. That was the torrential rain. I haven't seen one like that in a long time, so we were thinking, And it cleared in about half an hour. From our hill, where our viewing site was, it was some 10, 11 kilometers to the launch site, which is this white blip here. It was very muggy and steamy and hot. And then at 10:12, they started counting, and it happened. So here is the little composite of a bunch of frames taken by Charles Lawrence with the biggest lens I've ever seen in my life. And making a little 20-second movie out of it. It went up like a charm. I guess some of you have seen it on the NASA or ESA TV, which was better quality than this, I suppose, but this is an authentic picture by our own hands. Then they took us to lunch, and this is Jean-Loup Pouget, the principal investigator of the high-frequency instrument, Renaud Mandolesi, principal investigator of the low-frequency instruments, the 2 comprising the scientific payload, Charles Lawrence, Larry Wade. From JPL, for those who don't know. So that's it, it's flying, and now what is it about? This poster we put together at JPL some, a year ago, in an attempt to at that time, present the progress on integration of the spacecraft. This is before it was assembled. Various components of it can be seen there. But it shows an attempt at having a historical flight through what CMB exploration from space was. It was a COBE satellite launched in '89, following by WMAP, which is still flying in its 8th year now, and Planck just beginning its mission. That segment of the sphere is supposed to show the increase in quality of understanding of what's on the sky. So COBE was, of course, the spacecraft that allowed to measure anisotropy on the sky with angular resolution not exceeding 7 degrees. WMAP took it down to 1/4 of a degree. Planck's going to go to 7.5 arc-minutes. And kick in polarization at much better quality of measurement than WMAPs, as we will be glimpsing it momentarily. The story of CMB, of course, this began in '65 in experimental sense. These gentlemen shared half of a Nobel Prize in '78 for discovering the basic effect, which was the constant temperature all over the sky, signifying the early stage of the universe being very hot, very dense, very different from now, as indicated in the bottom picture of evolved galaxies and clusters. Understanding how it all comes together in the evolution of the universe is, of course, what our part of cosmology is all about. A further window on understanding was opened experimentally by COBE satellite, like I said, launched in '89. In '92, delivered results on anisotropy. Earlier than that, on the spectrum, electromagnetic spectrum of CMB radiation, awarded Nobel Prize in 2006, shared between John Mather and George Smoot. This is just a quick list, bullet points on importance of CMB. I suppose it doesn't need to be argued very much. It's a spectacular repository of information about early universe. It tells us a lot of stuff about as early in the universe as we can see and probe with electromagnetic radiation. And it's been explored for its energy distribution, signifying rejection of ideas on energy injection at high redshift in the universe, producing basically this beautiful black body curve as you have seen in measurement, as good as it's known in any measurements at all, better than in the laboratory one. And then our focus is on anisotropy, and WMAP, as I will show briefly, opened up that window significantly. Planck is the experiment that was designed to be the sort of closure experiment on temperature anisotropies, as I'll be explaining later. I will focus on just space exploration, and I don't want to make any injustice to people who do suborbital work in CMB. It's extremely important, and sometimes it even bites seriously at satellite work, but ultimately I think satellites, one way or another, always win. This is just a publicity diagram put up by WMAP team showing some crude rendition of time history of the universe for those who never cared to think about it, although I doubt there are any in the room. Up here, at present, we observe 14 billion years back to last scattering surface surrounding us on the sky, the moment, instant in the evolution of expanding universe when it became transparent to radiation. We can't see beyond that in electromagnetic radiation because everything, like the surface of the sun, becomes ionized and increases instantaneously pretty much. Mean free path of photons decreases it to 0, so we cannot see through it. But universe was, of course, in sort of embryonic stage at the time, so all the objects we see today at that time were not evolved yet, so we're basically directly probing initial conditions for structure evolution and for state of the objects as we observe it in the universe right now. This is a primitive slide just pointing out that we observe on a sphere, we observe a field of temperature or polarization variations. This is a scalar for temperature. We expand it in harmonic basis natural for a sphere. Those coefficients ILM, in theory, is describing what we expect to see are realizations of random Gaussian fields in a zero order of the theory. So most of the interpretative work invoking assumptions of statistical isotropy and rotational invariance of what we're looking at focuses on a single index function CL, the power spectrum of anisotropy, and that will be shown a lot. there are generalizations of that for temperature, from temperature to polarization and cross correlations and so forth. The basic concept is the same. What we will need later on, and I will briefly comment in the end, is that deviations from these fundamental assumptions of isotropy or Gaussianity of distribution of perturbations in the ensemble leads us to need the higher order objects than the power spectrum in analysis of the data. We're just entering that stage right now. Pretty much most of the CMB work so far was about as good a quality of power spectrum estimation as achievable. So briefly going back to Cosmic Background Explorer, this is what it looked like. The size of the spacecraft was about, I guess, 4 meters tall. Housed 3 instruments. The one of interest to us was the set of boxes outside the doer, 3 boxes comprising differential microwave radiometer, the instrument that measured anisotropy. And depending on perspective, if it's as skewed as mine, the most important result came out from that, as it simply discovered anisotropy. It produced a data set of 3 maps of the sky, or in fact 6 maps of the sky at 3 frequencies, duplicated each frequency, providing us with the possibility of subtracting them at each frequency from one another and measuring noise distribution in the sky very well. This was, as you can see here, in basic pixelization of the sky for the data, it was oversampled, so it's pretty noisy, and you work with the data on the sky that's noise dominated at most of angular scales. It's a little easier to see in an angular representation where the signal resides. Statistical analysis led to power spectrum determination like this. So up to about 20 multiples, you could measure reasonably well. Signal to noise was 1, somewhere around here. So what this plot shows is this CL coefficient that I mentioned multiplied by roughly L-square factor to make it flat on the plot, to render visually, I don't know, comfortably the scale invariance of the spectrum that has been found. Scale invariant would be perfectly flat. What Kobe found was a little tilted upward. And significance of this measurement, if you took a theory like this blue line and fitted it for amplitude only, if you fixed the shape and everything, just moved it up and down, it would be a 13 sigma fit out of Kobe data, okay? That was the significance of that early measurement. The other way of representing the significance of it was that ultimate processing of the data out of 2 better frequencies, subtracting and adding them, allowed us to produce pretty much the first rendition of the image of the last scattering surface that's ever been seen. So this is distribution of anisotropy, and this is the distribution of the residual noise of difference between those 2 frequencies, okay? After foregrounds were corrected for and so forth and so on. That was nice. It was about 3-to-1 ratio on a 10-degree angular resolution element on the sky. And it required a follow-up observation. Very difficult to obtain. WMAP had to do it because no suborbital experiments could measure any close to the whole sky to understand whether this was a solid result or not. So this is old stuff, but it pinpoints what I'm going to talk about later about Planck. So when those color bands show you the spectrum as measured, derived from the data, this plot reverses and shows in color a statistical spread around the theory that was most popular in the 80s, the theory that was matched to understanding at the time of distribution of galaxies in space, correlation functions and power spectra, invoked the concept of cold dark matter, which further had to be biased in a sense that baryon perturbations in gravitational potential wells of dark matter were shifted in amplitude weaker than the dark matter perturbations for various reasons that people invoked at the time. Its predictions were signified by this color band, and that's how Kobe measurements overshot those predictions. Okay, that was a bit of a surprise, which changed the course of theoretical work in cosmology instantaneously. What is very popular now is lambda set of models with cosmological constant. Their shape is different from the one I showed before. I showed you the blue line that was simply going down. This one has a little bit of a tooth going up at low multiples. This is a significant manifestation of the so-called integrated Sachs-Wolf effect, the effect of extra energy boost to photons due to, at some point, universe entering under lambda domination exponential drive towards exponential expansion again and suppressing gravitational perturbations in linear regime and contributing to energy of the photon as it travels from less scattering surface to us. It was measured insignificantly by CoBe. CoBe didn't make that claim. WMAP came up with that claim stronger. CoBe was so successful that we got very hungry for more, and basically in 93, a lot of action started mounting, which resulted eventually with WMAP and Planck as followers. And the idea was very simple. CoBe measured the sky with poor angular resolution and poor signal to noise. That was the state of the art of what was available electronically at the time. And we simply wanted to push it in the same way as just kind of traversing through centuries of exploration from poor knowledge 5 centuries ago to good knowledge of topography now. The coincidence I took that picture because that's actually a mathematical model of the topography of the Earth, which at the time was accurate to about 5 arc minutes, mathematically as a function fitting everywhere on the surface of the Earth. And this arc minute regime of temperature anisotropy resolution is somewhere where we wanted to take it from 7 degrees on CoBe, pretty far away. So the demands were acute, and it wasn't easy to go for it. This plot now in spectral, let's just look at the right side. In the spectral language, again, we have a CL coefficient multiplied by L squared. So now, if we look at logarithmic plot, this is where CoBe measured. This is where the spectrum is sort of scale invariant and flattish. When we go to angular resolutions below 2 degrees, we see features, so-called acoustic oscillations, which are residuals of evolution of the coupled baryon, photon, dark matter fluid, if you will, which is driven by initial perturbations in curvature, and at some point traversing through thermal evolution of the universe around the time of redshift of few thousand starts experiencing standing wave oscillations, which are phased in a certain way, which results eventually with abrupt dropping of opacity or increase almost to infinity of the mean free path for the photons with an instantaneous snapshot of these oscillations, which in a power spectral sense are these peaks. Okay, so when you take a specific model, take a Boltzmann equation coupled to Einstein equations, linearized, put some chemical composition of the universe into it, and so forth and so on, you can derive very accurately what these spectra should look like. And this is this holy grail of CMB measurements. Measure these as accurately as you can, then you can fit parameters which describe those spectra rather accurately depending on the quality of your measurement. The demands on your instrument are significant because this shows you what CoBe was. CoBe had 7-degree beam, so it simply killed all of this off, couldn't see it at all. It just saw the little bit of that regime, and it had noise, which was shown by this green curve. For those who get upset by noise not being flat, well, this is because it's L squared multiplied, okay? That's just the classic flat white noise on this rendition of the plot. So it was clear that if you want the satellite to, or any experiment, to measure these features, you have to drop the noise very significantly, and you have to open angular resolution. And this is what WMAP did in the first instance, going from 7 degrees to, say, 1/4 of a degree, with significantly lower noise, and Planck more ambitiously gave extra couple of orders of magnitude on this in noise and better angular resolutions. Now in linear plot, which shows better what's going on around the peaks, we can see the progression of noise curves for WMAP corresponding to integration from 1 to 2 to 4 years and so on. Right now it's climbing on this peak after 8 years. This is where low frequency instrument of Planck should be observing, and this is where high frequency instrument should be observing, opening measurement capability to loads of these features, and I will show the instrument properties further on in different degree of detail. So this is just a quick plot showing somehow the labels got dropped, but all you need to know is there are a bunch of parameters in each panel. As a function of L, various spectra are shown, and they respond to variations of parameters. That's what we want to measure. We measure the spectra, whether it's blue, or green, or red. We measure the parameters corresponding to it. That's the simple idea. This was so far about polarization. Of course, there is an associated effect of this was about temperature. There is an associated effect of polarization in CMB. Already in the late 60s, Martin Rees wrote the first paper, then others followed, observing that if you look at the conditions of the last scattering surface and imagine you're an electron, then relatively nearby field of photons irradiates you, and since you're not in a uniform medium, there are perturbations, you respond to quadrupolar moment of driving irradiating field coming onto you. That results with driving linear polarization in just constant sense. So scalar perturbations, even just the ones that lead to density perturbations, galaxies, clusters, and all of that, should have an associated polarization component in CMB. And it's small, it's only a few % of temperature in amplitude. Then people followed with Mark Kamionkowski among the leaders in observing that there are, of course, also in principle tensor mode perturbations in the universe, and they also drive gravity wave and related polarization perturbations, which have different topological properties from the ones I just described as E-modes. In fact, they should be considered potentially very interesting for measurement, because if they were found to be on the sky, they would indicate that directly there is a primordial field of gravity waves out there coming from the early universe. So this is the new Holy Grail, of course. A number of suborbital experiments attempted to measure that. There is no convincing measurement yet. Planck is often asked whether it will be able to do it. Opinions vary. I'm skeptical. I'll come back to that subject later. But maybe if we're lucky. We just don't know what the predicted signal is. This is just a quick snapshot of WMAP showing where it observes in space. It's a different configuration from COBE. I didn't emphasize on that picture of COBE, but you could see that it was on a near-Earth orbit. It was a satellite flying on a 900 nautical miles up in the sky orbit around the terminator of the Earth. It's still flying there. If you know where to look on the sky, you can see it every day passing overhead. Okay? It's not observing, but it's there. WMAP went to L2 space, Lagrange L2 point, not L2 space, which is a point co-rotating with Earth around the Sun, quite a bit further away than the Moon is around the Earth. And there will be a moving picture of showing how it works later on. It is important and good to be there because CMB measurements are all about thermal conditioning and stability in a low temperature sense. It's good to have all those three objects on one side of the sky behind the thermal shield because they're the hottest offending sources of radiation that can compromise your measurements of what you want to measure, which is of course a very faint signal. It observed differently from COBE, sweeping still significant fraction of about a third of a sky in observations during one day. It requires then ecliptic motion of half a year to reverse this pattern and pretty much close observations of the whole sky. So that's the natural cycle for us. All these instruments are not snapshot photograph kind of instruments. They're scanning instruments. They have a beam or a set of beams looking at the sky, and the motion of the spacecraft painstakingly measures and remeasures temperature at a point at a time. And only accumulation of this over time produces data that allow you to make images of the whole sky. It takes half a year to observe the whole sky. It takes a year to symmetrize the observations of the whole sky. I won't have time to talk about what that means, but that's what it is. So 1 year is good. WMAP had more frequencies, has more frequencies than COBE had, 6. Still, they're all on the low side of 100 gigahertz. Significance of that will be indicated momentarily. 5 frequencies, not 6. This is a composite map. So going from the lowest at 23, you can see that the galaxy, our Milky Way, is very intense at low frequency, becomes fainter as you go to the highest frequency of WMAP. These two were the principal cosmological channels for analysis. These were sort of foreground monitors to understand how to subtract galactic emission from the other two. This one is higher resolution, but more noisy than the other two and more complicated in beam response property sense. Well, this is a frequency-separated image of 3 offending sources of radiation that come on the sky as you observe cosmological anisotropy. Dust emission, which grows in frequency. Synchrotron, which is reverse, and kind of flat in frequency response, free emission. these three and more contribute to what stops you from outright looking at the sky and getting a snapshot of cosmological anisotropy. You can do whatever good job you want, you will still end up with some sky missing. The galaxy is much more intense than whatever outside of the galactic plane, so typically you realize in the end that you have to analyze something like this, that this is your best shot at telling people that this is a CMB anisotropy you're looking at, you still have a hole in it. Again, I have no time to go into technical details of how you do spectral analysis on that. There are interesting technical issues here. You don't have the full support on the sphere, but some of these problems are mitigated well, some not. Power spectral estimation is usually reasonably nice. So this is the WMAP CMB sky according to their analysis of foreground reduction and the power spectrum corresponding to it. So again, we've seen on COBE just this little bit. They have taken it to good few hundred, climbing on 2000, on towards the 1000, not much beyond, and that's where they're going to stay. The other thing other than temperature, if you heavily beam the data, it looks very nicely on top of the theoretical curve in temperature, and then you get into more challenging task of extracting polarization information. So as long as you do cross correlation of polarization and temperature, you still do reasonably well, and you see these oscillations, which should be phased in a certain way with temperature for consistency check. So the between black and red curve, you have a physical picture of what's linking these, okay? And then separately, you'd like to measure E polarization, the scalar polarization, also with its sequence of peaks, which should be shifted to temperature in a certain predictable way. You can see that measurements become a little bit more tortured, and the binning gets very heavy. And then there is the B mode, or the gravity wave-driven anisotropy, for which we don't have ab initio theoretical prediction of where to expect the signal. So this is just fishing in murky water. And they claim they have an upper limit somewhere here, which is not very impressive compared to what theoretical expectations are. This is where everybody's going to be going, if this field evolves any further. And Planck will get a better shot for the reasons just to be observed briefly soon. These are just old compilations of WMAP and suborbital experiments trying to show how nobody can compete with this on the full sky. So satellite just cleans this however it wants to. So suborbital people just go smaller angular scales. They observe smaller fields, integrate deeper, and match the spectrum at higher L's measured by them with what the satellite did. So this was the composite a few years ago, how far it was pushed. And this is another composite plot showing the same for polarization, which is at this plot, of course, is a pretty sad state of affairs of data thrown around without conclusion, although the measurement overall, if you know how to interpret this data, show significant better than 2 sigma measurements of polarization in E mode. So now all of that was laying ground for Planck, and Planck comes in. So here is the picture of Planck hidden inside the rocket. But that's what's hidden inside. So there were 2 satellites, as everybody knows. Herschel on top of Planck, with its largest ever astronomical mirror launched to space at 3.5 meters, and a pretty spectacularly sized dewar for liquid helium to support its observations for a couple of years. Underneath there is a cover within which Planck sits and waits. So they go up. About 20 few minutes into the flight, the fairing comes off. Herschel takes off on its route to L2. The shield gets shot off. 5 minutes later, Planck goes off. 25 minutes after launch, they're gone. Each on a separate way. These are a couple of pictures. One is a high-resolution, super-duper ESA drawing of the spacecraft. Very nice, mean, high quality, and it's just looking good. And this is what it actually looked like, photographed already in French Guiana before being mounted on the rocket. I'm showing that to appreciate the size of the satellite. So this is the stand. The satellite starts here. Or no, I'm wrong actually. No, this is not. This is all a satellite. It's even bigger. Planck has a large scope of science that it's attacking. It's described in this document that's distributed on the web, was printed also in an actual hard copy form, called Planck's Blue Book. It is a very wide scientific program for the reasons just to be described. Planck is a mission of the third generation for CMB measurements from space. Its original objectives were to pretty much clean up temperature and isotropy down to 5 arc-minutes. It comprises 2 instruments in a payload, high frequency and low frequency instrument. It measures temperature at 9 frequencies, polarization at 7 frequencies, not 6, as the slide says. It's the mid-sized ESA mission. Let me go through this briefly, but importantly. It's a European Space Agency mission. They provided the spacecraft launch system as listed, ground data system, mission operations, and so forth. Instruments, scientific instruments, were built and delivered by European international consortia. They were led for high-frequency instrument, are led by France, and for low-frequency instrument by Italy. Now, US has a very significant contribution to Planck. It's not necessarily always emphasized as it should be, so I need to emphasize it. Ultimate cost of the whole payload of Planck was around 600 million euro. About 100 million of that was delivered by NASA. 50, a little bit more than 50, is in hardware, and absolutely critical components of Planck, being bolometers, the actual detectors, the cooler, the redundant twin cooler built at JPL for the second stage of cooling on board, plus other components including the development of radiometric detectors. The other half of the money, a little less than half of the money, hopefully will be spent on sizable data analysis team that's distributed around the US, significant fraction of it in Pasadena at JPL, IPAC, Caltech, but also at Berkeley and elsewhere. So by no means anything to be shy about in a sense of criticality of contribution to. This is now the picture, the film, showing you the sun, the Earth, and the flight of Planck from the Earth, which is undergoing now, to its orbit around L2 point, which correlates here, okay, as I mentioned. And I'll show you another plot, which now, after making, so this is a version of the same movie, but after, oh, jeez. One sec. There we go. After it's already in orbit, so shows you a few more revolutions around the Lagrange point. Okay, so this is about 1.5 million kilometers away from the Earth, and the size of that Lissajous curve, that it's an irregular orbit around the L2 point, is about 700,000 kilometers. Okay, it goes up and down and so forth and so on. So Planck is then sitting on a point in the orbit, turned away from the Earth and Sun and the Moon. So these are behind the shield, spinning on the axis directed towards the Sun, and observing roughly on a circle on the sky, roughly almost on a great circle, orthogonal to the direction to the Sun, for thermal reasons. Now, this plot against frequency shows you the bands at which Planck will be observing. So these 3 up to 100 are the low frequency instrument. That's where COBE observed, and that's the WMAP observed. All of this is bolometric high frequency channels, which have never been used in space yet for observations of CMB. So this is completely unprecedented. This is where high resolution kicks in. Beginning with this channel, it reaches as low as 5 arc-minutes. Sensitivity, because of bolometric detectors' nature, is a factor of a few better than radiometric ones. So these are the points that signify improvements, dramatic improvements compared to WMAP, for example, based on which we should expect a much higher science return. This is a brief table showing characteristics of low frequency and high frequency instrument. Planck would have been even more special if it was fully delivered as originally planned. There should have been one more frequency channel at 100 in the low-frequency instrument, which would duplicate observations at 100 gigahertz, which would be unprecedented and extremely cool for rejection of systematics. Okay, well, for the meager €5 million on a $600 million spacecraft, European Space Agency dropped that channel. Italians ran out of money. US was supposed to build it. If it was built, it would be built in JPL and TRW. Unfortunately, we don't have it. So when you look from the top on the focal plane of Planck, you see this gaping, horrible hole here. This is where the 10 horns of 100 gigahertz would have been. The gold color is the top of the doer of HFI. So these little horns are higher angular resolution horns corresponding to these frequencies. LFI is just the orange stuff. So 70 gigahertz, 30, and 3 horns of 40 is what remains of low-frequency instrument. Low-frequency instrument would have been very competitive with WMAP on its own right. It had 100 gigahertz channel. Even if bolometers have failed, that was the original concept in thinking about Planck, that even if bolometers, which are risky, require more advanced ways of cooling the spacecraft, the payload, if some of that fails and just LFI remains in space, it would be a fully viable instrument on its own. Right now, with 3 frequencies, unfortunately, it's not. So, thank God, so far everything works even better than we expected. Hopefully, that whole consideration, but a pity is a pity. Cooling system. If Charles Lawrence gave you this talk, he would now take 15 minutes to describe it. I don't understand that in the same detail. I know it's extremely brilliant. Okay, there are some weak spots in it. The 4K cooler was the one that gave us tremendous headaches. This was built in England, and it stopped the launch by several months because it was discovered that it was leaking helium when the spacecraft was already integrated, and it led to tremendous headaches. If that hasn't been resolved a few months ago, we may have had a year delay or something. And right now it's in space, and pretty much a few minutes after it started working in space, it was clear that indeed the leaks have been mitigated and it's working fine right now. This is the picture of that famous suction cooler built at JPL. That's the second stage of cooling, past the passive cooling. Refrigerator without moving parts. That's all I'm going to tell you. And it takes it to 18 kelvins, and it's really good. So you have a spacecraft in space, you want to cool the focal plane, you want to cool the telescope. WMAP observes with the telescope at 90 kelvins. The passive system, devised with significant help in design from the US on Planck, should take it below 50 Kelvin already with just passive cooling. And that's where this cooler takes up job and gets it down to 18 kelvins, at which low-frequency instrument operates. Yeah? Yes, there is, but it's in the other coolers. This one passes hydrogen through the beds, but the other coolers, yes, the other coolers. Well, there is liquid helium which sits in the doer and cools the detectors, and there is and there is a dilution cooler helping to cool the HFI. Okay, so yes, I will show you the helium cables momentarily. I hope. Anyway, coolers, very nice. That's what makes tremendous difference compared to any other technology flown so far for CMB observations. Okay, gives you sensitivity gain by an order of magnitude. Now this is an ESA crude movie showing the spacecraft as it rotates. So as I told you, this is the shield. So Sun, Moon, and Earth are here. This is cold space. This is the shield around the telescope. The telescope, as it will show you momentarily, rotates on its spin axis and picks up. That's just a pathetic, of course, rendition of what it's doing, because we have about 50 horns looking at the sky, each of them separately maps. There isn't a contiguous region like this swept, but the best you can tell is that if you could reconstruct the focal plane has a pretty wide swath on the sky of about 6 degrees. So maybe that's the way to think about it. If you combine all the data from the whole width of the focal plane, you would be doing something like that. So now you're coming close to half a year of observations, and you're closing on the whole sky. And then you move on and you observe the sky the second time. Original proposal stage for Planck was only to do it twice. 1 year of emission, 14 months. To observe the sky 2 times, and that's it. And that was insane. And the liquid helium tanks hold enough helium to observe the sky twice for 2 years, which is still short mission. Let's not forget WMAP's observing already 8 years right now. We'll see. Let's hope everything works as the doctor ordered, and that will be enough. We'll have 4 sky surveys, as they call it. Now, what am I doing? Okay. So what Planck should return to compare to those COBE and WMAP data sets I showed you before should be a data set that ultimately will look sort of like this, an ecliptic frame from 30 gigahertz to 850 with the 6 cosmological channels over here, and those where the CMB is already weak compared to galaxy and point sources, mostly for pointed observations and different type of astrophysics, opening precisely those channels unavailable to the guys who observed only in this regime of frequencies. So we see synchrotron fading towards 100 gigahertz, and then the dust picking up and becoming the dominant source of foreground emission we have to fight with. The more frequencies you have, the better you measure them, the better chance you have to extract from those multiple frequency maps. Now this is diagrammatic of what we're doing. Something that by combination of data with astrophysical ideas allows you to reconstruct something that you tell people is a CMB map. You have to test it very thoroughly, but that's the idea. Then you do spectral analysis on it, and you go to cosmological parameters, and then if you're smart, you can go various ways, from maps to likelihood, from maps to spectra, maps to parameters directly, whatever. This is the part in which significant fraction of American team is participating very seriously, and this is the part which is hidden from immediate glory upon inspection. But what the cost here is that Planck will make these sky maps, as I said, at highest resolution, or 5 arc-minute resolution on the sky. This requires multiple million pixels on the sky for a single map. Now, we observe with a scanning instrument which is susceptible to correlated noise. Making maps out of that is non-trivial. If you have uncorrelated noise in a detector, you just co-add your data and you make images, okay? When you have correlated noise, you've got to do something about it. And the methodology of doing that is being developed for several years right now, and it requires very, very serious computer power, because some of those tasks, in ideal rendition, would require taking the totality of the data that we get, which is few terabytes of raw data, and analyzing that globally with covariances of all data against all data. It's just that's as simple as I can say that. And that's unmanageable on the biggest computer, so you have to come up with mitigating methods for analysis, and this is what we're doing. So we're making maps. We're happy with them to some extent. You're never really happy with them because there are approximations that go into them. So before you get the real data, you don't really know how well you did. This is from the old proposal stage plot showing what was the expectation of the ultimate result, heavily binned in L for WMAP, and compared with that of what Planck was going to do after 1 year of observation. So basically like by eye error-free power spectrum measurement to 2500. For a long time, I thought they overdid it. I didn't participate in that. I'll show you what the new version of that plot is. Polarization, considerably more noisy affair. So this is a composite plot, again, from various review articles. Let's see, WMAP sort of showing like no measurement, pretty much, just a little bit of it. And Planck with heavy binning to open up to 1,000 in E-polarization, and an open question on B mode. Now, for aficionados of mainstream cosmology and parametric description of a standard model of the universe and stuff, well, this is the kind of plot that they get high when they look at it, okay? So you get a bunch of parameters, kind of matrix, and contour plots on how well you fit them. This is supposed to show that if you take WMAP, you get purple plots. When you take Planck, you get red plots. Pretty much analysis by many people with best expectations for what the satellite's going to do indicate that most of the parameters that are used to describe standard models now will be measured at least by a factor of 3, some of them by a factor up to 10 better than with WMAP. That's just a quantitative statement. It's been tested in various ways. It's subject to ultimate performance in the data sense. We'll see. And then non-CMB science. above 100 gigahertz, I already mentioned that. Planck will be the only all-sky survey since FIRAS, one of the instruments on COBE. FIRAS observed, let's go to the next plot, with 7-degree angular resolution and didn't see a single point source on the sky, obviously. Planck will see 100,000 sources at a bunch of frequencies, and that's enough of a statement to say that all bunch of astrophysics will be opened up for investigation, something that's never been seen before. So let's look forward to it. Even if cosmology was not successful on Planck, that alone would be a brilliant output of the mission. Now back to the CMB sky for a little while. This is a simulation of temperature and polarization maps, just shown in linear scale, so to indicate how faint polarization is compared to temperature. And this is a power spectrum plot of the most sensitive channel at 143 gigahertz on Planck, 7 arc-minute resolution, 12 detectors looking at the sky, measuring 4 of them only in intensity, 4 in intensity Q and U. And all of these detector arrangements for measuring temperature polarizations are actually derivative of the very simple fact that originally when Planck was proposed, it was proposed as a temperature satellite. It hasn't been designed for polarization measurements at all. That came as a science case a couple of years later. So basically, instrument which was sort of being optimized for temperature measurements suddenly had to be redesigned when certain things were already frozen to measure polarization. So by no means at all is it an optimal or even near to that polarimeter. It's not. And the fact that polarization will be measured to some accuracy on a fraction of the sky will be a really good achievement, okay? So the way I look at the polarization situation myself is that the fact that we can measure E polarization very well is brilliant. B modes, well, let's see what happens. So this is the noise for temperature. And this is the signal for temperature. So clearly we get huge signal to noise. And then the interest in that plot is only because it actually goes through the full chain of simulations of the performance of the instrument with correlated noise included and all those, and some of the map-making algorithms we use engaged to produce the maps on which we compute the power spectra. So there is originally correlation, which is mitigated by map making to some extent, and the residual that you see is here. At low multiples, up to 2030, you see deviation of this orange curve from the faint dotted orange curve, okay? That's pretty much it. And for polarization, the noise is higher, it's in green line, and again, the straight white noise curve is exceeded by this deviation due to correlated noise. We needed to quantify that. We still didn't quantify that fully. It's very important for the following reason. When you look at polarization, the signal on the sky in the red is what you would see with no noise, okay? Well, clearly the noise at the most sensitive channel goes right through it. Some of the features are above the noise, some are below. There is this feature here, so-called reionization bump, which is excess power in temperature due to the fact that at a redshift of less than 20 somewhere matter gets ionized in the universe again, and that's how it physically drives the anisotropies, okay? So this is really good because it says that suddenly and this is what WMAP said is on the sky, okay? It needs to be confirmed by someone. If this is the case, this is normalized to WMAP claims of what they have measured, then we'll have a factor of a few of excess in power in polarization above the noise. And if it was as good as this plot shows, even these residual correlations, sorry, it's the green versus purple that you should be looking at for polarization, even by eye you could see that signal, okay, and then quantifying it phenomenally for parametric estimation would be another matter. Well, that's where we do exact covariance analysis of residual noise, and it's an ongoing and very painful task, okay? We'll see. But here, you see by eye the imprints of those extra peaks. When you co-add the 3 frequencies of the highest sensitivity, central at 143 and 2 on the side at HFI, the whole picture gets amplified a little bit. So basically, E-mode polarization should be discernibly good just by eye. Quantitative analysis is still ongoing. This is the compilation of, at the same time, ongoing suborbital measurements showing how far people took it with an Akbar instrument for temperature measurement. So that looks pretty good and goes where. So this is the range that Planck should be measuring. You've seen that. Planck should be measuring that, you know, without noise. And then, significantly, a quad experiment returned results from South Pole on polarization, where here only 2 sigma points are plotted, and it looks pretty good compared to theory. So this is what we're against, and the question is, there is always a question, has the satellite been already scooped by these guys who are working extremely hard? So what are we going to do better than them? This is the same binning for temperature for Planck in the light blue dots. And this is the same binning as on the quad plot for polarization. So I think we'll do relatively well on it, up to 1,000. Advantage, while they measure on a single patch of the sky more significantly per pixel, that's a very small patch of the sky. So sampling variance has to be taken seriously into consideration, and measuring the whole effect on the whole sky will certainly not hurt. It will stabilize our knowledge of polarization. So Planck's now on the way since 14th of May. Every report we've got so far is brilliant. Not a single worrying sign so far. Thousands of comments issued to the spacecraft, and it's responding beautifully. Everything is just working like a charm. So assuming that this is what the situation will be for the next 2 years, what we'll end up with will be indeed the mission that will have cleaned the temperature anisotropy, will establish the knowledge of the universe at redshift about 1,000 that will be amazingly, in accuracy, better than at redshift 0 in cosmological sense, because the spectral measurements of temperature distribution will actually beat the painful process of accumulation of knowledge in galaxy surveys and accuracy of it. So what has resulted from it all is that development of Planck was sufficiently long that it also became, in some sense, a prior in assumptions for next generation missions. And let's hope that it will deliver on it, especially the CMB Pole mission, which is now being conceptualized for specifically optimized design for polarization measurements. If that ever comes, we'll see. Now, I mostly referred to, in crude way, to significance of the spectrum measurement and what it links to. A couple of aspects I wanted to raise now before the end of the talk that will take us beyond the power spectrum and Gaussianity and all of that. So one is non-Gaussianity. Some of you may have attended a talk by Ben van Delt, who's on the Planck team, and he's now on sabbatical here at Caltech. And about, 2 or 3 weeks ago, he had a talk where he specifically, I think, talked about that. It emerged in analysis of WMAP data that people started claiming significant measurements of spectral quantities beyond the power spectrum, like bispectrum, okay? Corresponding to 3-point function and correlation function sense, which are quantities which for Gaussian theories of distribution, statistical distribution of perturbations should be vanishing. So if you would measure any of them, it would be significant because it would inform you on the process that generated initial perturbations and whether that process corresponds to the simple renditions of some inflationary theories, which in the mainstream are assumed to be Gaussian distributed in perturbations they generate. That's a controversial field right now. What has happened is that several groups ran results on WMAP data, claimed disparately either significant measurements or just upper limits still from the last edition of WMAP data. What is positive about that is that a lot of hard work went into understanding how to very carefully conduct these analyses and analyze propagation of systematic effects. Okay? That will be very useful on Planck. And understanding how Planck's noise performance will improve error bars on these quantities. So we know for sure that if there is any non-Gaussianity of the type that was speculated about in all of that line of work, then Planck will measure that 5 times more significantly than WMAP allowed it to be done. And that's a very good prospect, and it became a relatively prominent aspect of the science case right now, slightly underlooked before. But that's just the area that evolved very recently and was driven specifically by the delivery of the WMAP data and analysis that followed. Another, even more fundamental aspect well, I don't know, about even more fundamental, equally fundamental aspect of what's going on the sky is how far are we taken with these sort of measurements towards revisitation of the old question of what's the story with isotropy of the universe. In a sense, CMB allows us to make the most stringent statement of how isotropic universe is around us. An implication of that is important because it limits very severely the almost uncountable variety of pure general relativity models that you could invoke for global cosmology. So if the universe is indeed very strictly isotropic, well, that limits the options available for pondering viable cosmologies. So in the line of work that was multi-threaded, I participated in one of those. It's been determined that if you look at the sky as measured by WMAP, something weird's going on. And if you start generalizing your statistics for measuring distribution of perturbations on the sky in such a way that they are direction sensitive, so you don't estimate just globally the power spectrum on the whole sky, but estimate it at few areas of the sky, okay? And see, does it vary from place to place? And very crudely speaking, opposite sides of the sky in a certain orientation indicated on this top plot here by equator corresponding to it seem to indicate that there is more power action on one side of the sky than the other. Sounds a little silly, but it's quantitatively measured. In the first instance, we have found it out in our work with first year of WMAP data already on the level approaching 3 sigma. After 5 years of WMAP data, we clearly exceed in all estimators we have used a very comfortable more than 3 sigma range. And other people measure it in a different way, and the results are consistent. So what's going on? We have written a silly, well, not silly, funny paper where we fitted in the tradition that has been propagated since before COBE, the Bianchi models to the sky. Bianchi models are, of course, prescribed, deterministic, non-isotropic cosmologies, which, if you propagate photons in them from last scattering surface, generate amazing patterns of anisotropy which are not statistical, they're deterministic given the parameters of the model. So fitting something like that to the sky is complicated because the library of models depending on, say, 3 parameters is pretty wide, and then you have 3 Euler angles for rotation of this thing on the sky. So computationally it's kind of painstaking. But we fit significantly some models to the data. And after we fit them, you could see why. I mean, that these are constellations of hot and cold spots on the sky which fit the features of the model. All of that makes no sense physically because this model is an open model superimposed at low L's with all the structure which is not on this plot, which fits the standard flat cosmology very well. So the hybrid doesn't work in any way. It's simply supposed to indicate that there is something on the sky that could be described by deterministic pattern that fits significantly. Now, is that important? Well, depends how you think about making cosmological measurements. If you think that universe has to be isotropic and then you do everything to prove it and you reject what doesn't conform to it, then it's unimportant. If you are open-minded and you see on the sky something that looks surprising, well, you should give it yourself a pause. I'm not going to push it any further. Planck will take a look at that. And will, like with COBE versus WMAP, confirming the overall structure of anisotropy on the last scattering surface, that will be one of the first things we're going to look at. And then we'll know whether WMAP screwed up, had something in the data that nobody has discerned after 8 years of torturous analysis trying to explain this. Well, we published this result, and after 1 year of observations, they hated it like hell. And they tried to do everything humanly possible to say that we were wrong, and there is everything right in the data. And then after 3 years, they confirmed it themselves in the 3 years of data. So it is on the sky. There is no doubt about that. Nobody knows what the interpretation is. Some work came out of Caltech here as well on the beginning of the theoretical speculation on how some alternative inflationary models could produce this sort of features. Let's see what happens. Parting shot, this is only a subset of the Planck team. Imagine that, okay? So this is, I don't know, some 200 people in that room. The whole team is, I don't know, if you integrate over time, over those 15 years, it's probably 500 people have been involved. this is mostly the kind of crowd that's going to participate in data analysis rather than instrumentalists. This is from the meeting in Bologna a few months ago. And the final parting shot for you. Planck fanatics at their best. This is a picture of Planck going to L2. There it is, if you can see the dot. Read it. You can photograph the sky. You can see it. It's going to reach L2 in about under 3 months of the cruise. We expect to start observations in mid-July. And hopefully everything will be as advertised to you, and you'll enjoy the scientific results and the presentation to you later on. And now I'm going to perform a strip to the much better looking Planck.